engineers of today, uh, the Mechatronics series. So we're going to continue learning about the Raspberry Pi. However, I'm actually going to make a small, we only have a couple lessons on it, but I'm not necessarily certain we're going to be able to get through each lesson in one day, but we'll get through them as quickly as we can. We're going to make a small diversion into Scratch. And that is because, A, maybe not everybody has received their Raspberry Pi yet. B, when we do start using them, they are going to assume at least a baseline knowledge of Scratch. Or at least it would be very useful to know that kind of stuff when you're working with it. So for that reason, we're going to go ahead and get started with it. Now, I'm sure that a lot of you are probably already pretty familiar with Scratch, or at least have heard of it, or have had some exposure to it. So, this is going to be a little bit of a review as well, but it will be good to get some review, certainly, before we get started on things. And obviously, if you've had no experience with Scratch, then getting familiarized with it will be incredibly helpful. So that's going to be the focus of today, and at least the next one or two lessons. How's everybody doing, by the way? You had a good couple of days? Well, I hope so. Okay, so without any further ado, let's go ahead and let's get started with Scratch. So the nice thing about Scratch is it is available entirely online. We can go to scratch.mit.edu, which, again, you may already be familiar with, but I'm going to go ahead and put it into the chat box anyway. Just go ahead and follow that link, and you'll be able to, you'll go to Scratch's site. You'll be able to create a username if you don't already have one, or log in if you do. Excuse me. So this is Scratch's website. If you haven't ever messed around with it before, it is a free and very easy to use programming language. I mean, all programming languages are free, but this comes with a bunch of resources and stuff like that already built in. In addition, you can check out other people's projects, and you can also, look at their code and see how they've done it and stuff like that. And there are resources like what's the word I'm looking for? Sprites and things like that that you can use for your own projects. Plus, it's very easy to import resources for your own projects as well. It's just a very easy to use program. So what I'm going to do is I'm going to go ahead and click sign in. But if you don't already have one, you're going to click join Scratch. Create a Scratch username and a password. And there are a couple other steps in the process. I believe it's email address and date of birth and things like that. If you are younger than 13, I believe you will need parental permission in order to create projects on your own. If you already have a username and you've already done that, obviously you don't have to worry about that. If you have not, though, and you're younger than 13, that's just something to keep in mind. But I'm going to go ahead and sign in since I already have a username. I'll give everybody a couple of minutes. Raise your hand if you have to create a username if you don't have one already. Okay, a couple of people. So I'll give everybody like 5 or so minutes to get that set up before I continue, just because I don't want to leave anybody behind. If you are creating one, just go ahead and raise your hand when you're done, just so I have an idea of when to continue. I believe we're waiting on one more person, so I'll go ahead and give you guys a couple more minutes before we continue. Okay, let's go ahead and continue. So I'm assuming at this point that you've signed in and that you're currently looking at a screen that looks like this. This is the Scratch basically home screen. As you can see, if you're following anybody, you can see any projects that they've created recently. There's Scratch News, which is just basically general information from Scratch. It might be good to know, announcements and things like that. We got a list of projects made by other people, obviously all down here that you can check out if you're ever interested about any of them. If you're ever looking for inspiration, you can check these out, and you can see the code that goes behind it so that you have an understanding of how they did what they did, which is another great thing. But right now, what we're interested in is this one tab at the top labeled Create. This is what you want to click on anytime you want to make a new Scratch project from, well, Scratch. But yes, this is where you'd like to go. And this is the editor screen for Scratch. There are a few things here. I just want to go ahead and run through all of these just so you guys know what you're looking at. So up here in the upper left-hand side is the view window. This is what the program looks like whenever it runs. This is what people will see when they run your program. This is essentially the output. And this is where you'll be able to see all the results, of all your hard work. As you can see, we've just got the one cat in there right now, the Scratch cat, but he's just a placeholder, just so you have something to start with. Directly beneath that, we've got a list of all of the sprites that exist in this Scratch program. Well, certainly in this stage at least. Right now we've only got one. No surprise there. It's the Scratch cat. He's labeled Sprite 1. But here we'd be able to add new sprites if we were so inclined. We could add sprites from a library of sprites that Scratch has. We could paint our own. We could upload one from a file. We could take a picture and use it. In addition, we can edit it by, we can show where it is on the screen by double-clicking it, and then edit it over here in costumes. We'll go over that in a moment. Then to the left of Sprite 1, we've got this thing that says Stage 1 Backdrop. Backdrops are literally what the background looks like. So, that's good for change of scenery in case, you want to have some sort of progression or something like that, like different levels might have different backgrounds, or if you want to have just one static one to serve as a backdrop for whatever you're looking to do. But that's where you'll find information and the ability to edit that. So again, we've got another set of 4 buttons down here where you can choose one from a library of backdrops that Scratch has. You could draw your own. You could upload one from your computer, and you could take a picture and use it as your backdrop. So again, you have essentially the same options. But that's pretty much everything that's going over here on the left-hand side, going on over here on the left-hand side. Excuse me, coughing fit. Now, everything from this line over, this is where the bulk of the work happens in Scratch. Over here we've got the code blocks, we've got the block editor, and we've got some tabs up here which we'll check out in a moment. But what I want to call attention to right now are these code blocks. These are how Scratch is written. It's literally all just dragging and dropping blocks and snapping them together like Lego. So, if you're ever wanting to make something, you can just take the various logic blocks that they have here and snap them all in a specific order. Now, you'll notice that it doesn't seem like a whole lot, but that's just because this is one category out of all of the possible categories for code blocks. If we clicked on maybe looks, as you can see, we can get a whole new set of blocks. And they're all color-coded as well. Sound is going to be sort of a pinkish kind of thing. I don't know why looks, more blocks, and sound all have such similar color, as well as motion and sensing. But hey, who's keeping track? Anyway, sound has this light pinkish, purplish kind of thing going on. Looks has the darker, and then more blocks has like a royal blue. Anyway, motion if you want to affect the motion of a sprite. Looks if you want to change visuals about it, maybe make it look like it's saying something or change a costume or anything like that. Sound for your computer to play sounds. Pen for a drawing on the screen and things like that. Data is interesting. This gets into variables, which we'll cover as we continue with Scratch. But variables are a very important part of programming, and the more comfortable you get with them, the better off you'll be. Events are sort of triggers that make things happen, which sounds incredibly vague, but again, that'll make more sense as we go along. Control. Control is meant to affect how a program flows. So if you want a program to flow differently from one run to another based on what happens, what the user does, maybe you want it to repeat itself, things like that, that'll all be on the control stuff. Sensing looks for either input from the user or reactions with other sprites or the backdrop. So there's a lot to be done in sensing as well. That's sort of like the input part of the input-output. Operators is where we do a whole bunch of math, and don't get me wrong, there is a fair amount of math in programming. So again, the more familiar you can get with math, the happier you'll be. But it's interesting how programming does it anyway. And then more blocks, which is just if you want to create custom blocks, which is something that you don't necessarily worry about, and you certainly won't right now. It's just as you start to become more confident and comfortable with programming and you realize that the blocks that Scratch provides aren't exactly fulfilling your needs. So if you find that that's something that happens, well, you can always give more blocks a try to see if that helps you out. But this is all the scripts part, which is where all the programming magic happens. Now, let me go ahead and click on one of these tabs up here. How about the one labeled Costume? Costumes are the aesthetics or the look of your sprite. You can keep the same sprite, but you can change how it looks in order to give it a sense of animation. Now, this will be wonderful when I stop coughing, finally. Now, this is not necessary in order to make a program run. You don't need costumes in order to have a fully functioning program. You can make a program where nothing switches costumes or anything like that. But, as you can see here, I click between costume 1 and costume 2, and it kind of looks like his legs are moving and he's doing like a little bit of a walk that's like partially completed. If you spend the time to add new costumes in sort of an animation kind of a sense and make it so that your program switches between them as it's doing something that makes sense with the animation, like give them a little walking animation and have them walk to the right side of the screen or something like that, then it goes a long way towards making your program look nicer. Now, yeah, again, not strictly necessary and probably not something you guys are ever really going to mess with a whole lot when you're working with Raspberry Pi. I can't say I'm terribly familiar with what the competition's going to cover, but I imagine it's going to be more on the hardware side of the Raspberry Pi, so you're not going to really have to worry about, making costumes for random sprites and stuff like that. But regardless, it's there for the future in case you're ever interested in working with it. If you ever want to continue with Scratch later on. So that's costumes. And then sounds, well, sounds are just that, sounds. Pretty self-explanatory. If you ever want a sound to play, probably want to make sure that it's added to the sounds tab if it's not one of the ones that's listed by default in the sound block of scripts. So you can see here, play sound meow. It's referring specifically to this one. There it is again. That wonderful meow. Sorry, I didn't quite get to the mute button in time there. If you ever, again, this is just another one of those things that helps to make your program more fleshed out and more refined looking, but probably not something you're going to mess with in the competition. So anyway, let's go back over to scripts. Because what we want to do is we want to make our first little Scratch program. And we're going to cover basically a few aspects of the Scratch program, and I'm going to spend some time talking about like programming fundamentals and stuff like that so that you guys can understand why Scratch does what it does and how it relates to programming in a more general sense. Because, it's good to know why things happen the way they do and why you might want to do something over another thing. I mean, that's kind of the whole point, isn't it? But anyway, we're going to get started with something very, very simple. In fact, it's so simple, I need to double check on how simple it is. Yep, very simple. This is going to be your hello world of Scratch. So under the motion category, as you can see here, we got a whole bunch of stuff. Move 10 steps, turn 15 degrees, turn clockwise 15 degrees, turn counterclockwise 15 degrees, point in direction 90, point towards mouse pointer, go to X, 0, Y, 0, go to mouse pointer, glide 1 second to X, 0, Y, 0, change X by 10, set X to 0, change Y by 10, set Y to 0, if on edge bounce, set rotation style, X position, Y position, direction. A whole bunch of stuff. These are all different things that either affect or store the position of the sprite on the screen. It's also important to note that each sprite is going to have their own set of scripts. This is, in a sense, kind of like an object-oriented scripting language, which is strange. That doesn't mean anything to you, but maybe you'll remember that particular phrase and think about it in the future and go, yeah, that is kind of weird. But anyway, regardless, what we're going to do is we're just going to make the cat walk to the right as he's saying hello. That's it. That's all we're going to do. It's going to be very easy. Yeah, listen to me yawning. It's so simple. Apologize. Just haven't had enough coffee today, apparently. So what I'm going to do is I'm going to bring out my first command just by clicking and dragging and place it in the big editor area over here. And that command is just move 10 steps. What do you think move 10 steps is going to do? I mean, this is not a trick question. Well, move 10 steps is going to make him move 10 steps. Okay, so what do steps mean exactly? Well, if I put my mouse cursor inside of this view screen on the left-hand side, just underneath it, you'll see that there is a set of numbers preceded by an X and a Y. These are coordinates. How many of you, show of hands, have already started with algebra? Okay, a couple of hands. Not everybody, but a couple of hands. So for those of you, you guys are familiar with coordinate systems then, like graphs and stuff, perhaps, if you've gotten there. Those of you who are not, graphs are sort of, well, they're drawn representations of mathematical equations, essentially. And the way that that's done, you've probably seen graphs used. I mean, it's not like graphs are a totally foreign concept until you get to algebra. But the thing is, algebra kind of starts to take into a whole new level before things really start getting crazy in other mathematics. But let's assume we have a couple of lines here. And these lines are meant to help us keep track of the position of everything on the graph. If you've ever messed with graph paper, it's a whole bunch of squares, right? Well, those squares are meant to make it easy for us to be able to draw consistent lines that represent mathematical equations. So, for instance, you might, want to draw something that's like 3x minus 4 and, draw a line on the graph that represents that. But that doesn't mean anything if you don't know x. It doesn't mean anything if you don't know why. Well, why you're doing it is because you want to get a sort of a visual representation of the equation. But I'm getting ahead of myself. The way you denote where something lies on the graph is with a set of coordinates. Show of hands, how many of you play Battleship? Okay, well, a few people. Again, not everybody, but the whole idea behind Battleship is you have like a grid of squares, and then you put your ships down on the grid of squares, and that's where your ships are. And you're playing against somebody who does the same thing. But neither of you can see the other's board. So you have to guess where their ships are by the idea being you're shooting shots like blindly trying to figure out where their ships are and then kind of narrowing down where their stuff is. But in Battleship, generally they're 10 by 10 grids. So whoop, 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 whoop. This is not 10 by 10, but you get the idea. And their ship might be right here. And if you're trying to guess that area, you can say, oh, the second one over from the left and the second one from the top. But that doesn't really, that gets kind of annoying, especially if, let's say theoretically, the battleship grid was 100 by 100. Then when you're saying like, oh, the 54th from the right and the 67th from the bottom, that becomes incredibly cumbersome, especially because that would be the most absurd way to announce the positions. Anyway, the way they get around this is they have names, whoops, for each of the rows and each of the columns. I did that backwards, but each of the rows and each of the columns. So now let's say I wanted to try and hit here. I could say B2, and my friend that I'm playing against would be able to know exactly which square I'm talking about. So in that sense, it gives us an easy way to refer to each position on the grid. With a graph, similar kind of idea, except one direction is x, and one direction is y. As we go more to the right on the x-axis, the numbers get higher. They start at 0 where they meet. So this right here is 0. But as they go higher on the x, the numbers get higher. As we go this way, the numbers go below 0. They go negative. As we go up on y, the numbers get larger. As we go down on y, the numbers get larger below 0. So in that sense, this would be x1, this would be y1, this would be x2, this would be y2, and so on and so forth. It's a pretty simple concept, but it allows us to say like, oh, okay, so I want to place a dot at x4 and y -3. So we can actually count that out. Okay, so x4 and y -3, and bam, we can put a dot exactly there, just like in Battleship. Well, a computer screen has like a bazillion pixels in it, right? Like a whole jillion ton. It's the official term. So we need some way of keeping track of where those pixels are, especially when we're programming, because if your programming gets if your programming gets complicated enough, eventually you're going to be telling the computer where to place individual pixels. And we need some easy way to do that. You can't say, okay, place a pixel that's green in the area that is the 347th from the left and the 659th from the top. Because the computer has no problem keeping track of that. But man, that's going to be a pain for us. Plus, that's just kind of weird to say it that way. So what we do is we just place a graph over the screen. Well, let's do it this way. Over the screen. And now anytime we want to refer to a position on this screen, we refer to that invisible graph that exists there. So that's what these x and y numbers are. They're coordinates on that invisible graph that exists on the view screen. And as I move the mouse around, I can see that they get all kind of crazy and change around and stuff like that. Like if I try and keep my mouse very still horizontally and just move it vertically, I can see that the y is changing a whole lot more than the x. Obviously, I'm not keeping it perfectly still horizontally, but I am moving it much more vertically than I am horizontally. So you can see that the y is changing a lot by like large values. And I move it horizontally a lot and try and keep it in the same place vertically, the x is changing a lot more than the y is. So there you go. It's meant to give you a basic idea of where your cursor is on the view screen. So when I say move 10 steps, basically we're just adding 10 to the x position, the horizontal position of the cat. That's all we're doing. Now the steps thing is relative. The only reason it's moving 10 steps in the positive x is just because that's the direction that the cat is facing, but we're not really going to worry about that too much right now. We're just gonna say he's going to move to the right 10 steps, 10 in the x, and call it a day. So there we go. There's our first command. Now we're going to go over to looks. After I took long enough explaining that stuff, we're going to go over to looks, and we got a whole bunch of stuff here too. You got say hello for 2 seconds, say hello, think for 2 seconds, think show, hide, switch costume, next costume, switch backdrop, change color, set color, clear graphics effects, change size, set size, go to front, and go back. This is all things that affect the visuals on our sprite. Other than the position. The position's all going to be in motion, but visuals that are not related to the position are going to be in looks. So, yeah, sure, I'll ask this. Why do you think we have change color and set color and change size and set size. Why do you think those exist? Why do we have two things that affect the color and two things that affect the size? Well, it has to do with basically relative versus absolute. What do I mean by that? Well, basically just change size by 10 means that we're going to add 10 to the size value to whatever it was before. So if it was at, 90, it will become 100. Set size to 100, we'll set it to 100 no matter what. So again, if it was at 90, it will become 100. But now, since it's relative versus absolutes, we have more flexibility. So let's say the size of the cat varies wildly from 10 to 200. If we wanted to reset the size back to 100 every time we're done with the program, we couldn't reliably use change size, could we? Because we don't know what size the cat is going to be at the end of the program. It could be 90, in which case we could use change size by 10, and bam, it's back up to 100 just like we anticipated. But what if it's 80? Then we change size by 10 and it becomes 90. All right, so we just use change size by 20. So 80 becomes 100. Boom, done. What if it's 110? Well, it becomes 130 then, and now you got a problem because the cat's too big. So you change size by negative 10. 110 becomes 10. Bam. All right, fine. The problem is you can't change that stuff while it's running. And if you can't anticipate what size the cat is going to be by the end of the program, you might be better off using an absolute, like set size, which will change the size to 100 no matter what size it is. If it's already size 100, it'll just get changed to 100. No harm, no foul. Nobody can tell the difference. But it does ensure that we have consistency. On the other hand, change size, a relative one, is good for, if we were to use an example, like a hero is running through a dungeon and he picks up a health pack. It could be a small health pack, so it affects his health by 25% or her health by 25%. So we'd probably want to add 25 to their health. We couldn't just say set health to 25% because, that's not going to help. It's great if they have, 5% health and then they pick up a health pack and suddenly they're at 25%. It's horrible if they're at 100 health and they go and pick up the health pack and now they're at 25% health. So, there's a time and a place for each one of these. And well, it may not seem terribly useful to know now, it's a concept to become familiar with as you get more proficient with programming. Now, for us, for our first program, we're just going to say hello. We're going to have the cat say hello for 2 seconds. And that's it. That's all we're going to have him do. So we're going to have him move 10 steps and we're going to have him say hello for 2 seconds. However, we need to make sure that one happens after the other. Specifically, we want to make sure that he says hello after he moves 10 steps. The only way we can ensure how things are going to be ordered in Scratch is by just attaching them together. You'll notice how there's this tab and then also sort of a slot on each of the blocks. Well, they're meant to stick together, like so. So now, the say hello for 2 seconds is attached to the bottom of move 10 steps. And the way Scratch reads its scripts is always from top to bottom. So anytime we're going to be running this program, the cat is going to move 10 steps first, and then the cat is going to say hello for 2 seconds. And that's it. Well, almost. Let's go ahead and click the green flag and see what happens. You might get nothing, right? In fact, it may not even seem like anything happens, like you can do anything, like if it's registering whether or not you've clicked the green flag. Like nothing is happening. Now, this is because of a pretty important concept that you guys will become very familiar with and that you guys will deal with a lot throughout your time spent coding. This concept is something that just, is inescapable and is always going to be popping up again and again in various ways. And it goes something like this. Computers are dumb. That's it. Computers are just super dumb. Computers can do math so much faster than we can. Computers can predict weather patterns and keep track of all of these individual sort of nodes and give this wonderful, graceful, movement, swirling movement to them and move them across a map, and we can use that in order to predict the weather much better than we can normally anyway, and they can be used to readjust a plane's flight course in small increments from moment to moment, and they can even just keep track and watch the fuel mixture in a car and adjust the way that it intakes air or takes in air, again, on a moment-to-moment basis, much faster and much better than humans can. But humans have a few advantages over computers, and that is computers can't do this stuff without humans telling them how to do it. We're the ones who write the programs for the computers. Computers haven't gotten to that point yet where they can write their own programs. On top of that, they're very, 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 very explicit, and things kind of fall apart when they don't fit into that explicit sort of box that computers need to have. For instance, let me just do this real quick. Let's say we tell a computer that this is a word we're interested in looking for. Cat, the capital C. Now, after that, we feed the computer a list of words and ask it if it recognized the word that we told it earlier. And we say dog, bird, cat, lion, mouse, puma, lynx. You think that computer will recognize it? Raise your hand if you think it will. Raise your hand if you think it will not. All right, so some of you have gotten it already. Do you think you know why the computer won't recognize it? Just go ahead and throw it into the question box if you have an idea as to why it won't accept it. It's not the name of the sprite. All right, all right. It's not in the proper language. Okay, okay. Aha. Is it Aishwarya? Yeah, and yeah, all right. And then Martha got it as well. So, yeah, basically, okay. So we can recognize the word cat because the word cat has some sort of intrinsic meaning to us that we can just sort of like, okay, I've read this word before. I know what cat means, and then it's attached to a picture of a cat in our heads, and there's an emotional sort of feeling behind the word as well. We think of a cat. We might think of a cat that we have. Um, we might think of this one neighbor cat one time that took a swipe at us. Who knows? But there's usually some sort of, well, okay, there's that too. I mean, I was assuming that we had, but that's a very good point, Ved, and exactly, Victor. You got the idea too. Um, but like we understand language, and we understand the meaning behind words, the meanings behind words, and things like that. And we can. There's that too. We can recognize, even if we saw that, we could go, okay, that could be a person's name, or that they could have just misspelled cat, like as in the animal. We have the ability to infer and draw conclusions from limited information. Computers can't do that. In fact, if we haven't told them that a lowercase c is the same thing as a capital C, they're going to look at this. They're going to be like, I don't know what that is. Doesn't look like this. So it's not the same thing. And it's strictly because of that capital C. Computers are incredibly explicit. Now, in addition, if we told them, hey, um, these are what cats are, like, here's a cat, I want you to find all of the cats that are here. And technically we've got cat, but we've also got lion and puma and lynx. And the computer is not going to be able to figure that out either. It's going to go like, a lion is not a cat because it's not a cat, and a puma is not a cat because it's not a cat. Like, that's about as far as it's going to go. Whereas we can go like, okay, I know what a lion is, and technically it's a big cat, so hey, that's all I needed to be told. So if somebody said, hey, point out all the cats here, you could go, oh, cat, lion, puma, and lynx. Yeah, exactly. You need to state in the code if the lion is a cat, and so on and so forth. Um, computers don't have that ability to sort of draw conclusions from multiple disparate points of data like we can. We could sit here and be like, okay, so like we can look at a picture of a lion and we can go, hey, wow, that looks a lot like a cat, like a really big cat. Maybe it's a type of cat. We can make those conclusions ourselves. Computers cannot. They can't sit there and look at a lion and go, all right, well, it's got paws like a cat, but they're just really big. And it's got fur and sort of a general body structure like a cat, but it's just, a lot of it. Maybe it's a cat. No, it'll just go like, lion. It's an animal. But because you told me it was an animal. So in that sense, computers are very dumb. We have to be very explicit about everything. In this particular sense in our program, the reason why nothing's running is because we haven't told it where the program starts. It seems pretty obvious to us, right? It should start at the top of the only code that we have in this entire program. That would be, you would start, yeah, and actually that's a good point, Ved. He said you could list all the features of the common cat, and the computer might recognize one when it sees one. And that's actually what a lot of AI researchers and computer science, computer science doctorates and people like that, all these fancy people, that's what they're trying to get computers to do now. It's actually been a long and hard road because a lot of it has to do with the fact that we don't quite understand how we draw conclusions ourselves, how we recognize things and how we do things in that manner. Like, part of that is you could write a class called cat, but you would also have to, that would involve more defining a cat from scratch and then creating definitions for those other things from scratch too until that would be a that would be another discussion for another day. But in essence, writing a class called cat would essentially let the computer know that there is a class that exists called cat, but it wouldn't necessarily give it the tools it needed in order to recognize what a cat is. Even though we could be incredibly exhaustive in our definition of cat, um, it would be a good first step, but Overwatch, what about Overwatch? Oh, gotcha. Yeah, all the common features of a tank. Yeah, yeah. So the tank is a class of character in Overwatch, or a category of character in Overwatch, and yeah, yeah, exactly. Like the large target, lot of health, um, you know, defensive abilities. Wouldn't artificial intelligence be considered to be able to find the cats? Specialized artificial intelligence, certainly. That would be yeah. How would you know, Victor? um, yeah, figured as much. Um, that would be like sort of a form of specialized artificial intelligence. Um, we're at the point now where we're trying to figure out how to get a computer to recognize cats or dogs, I believe. And then once you've succeeded at that, we will have an artificial intelligence that is able to recognize dogs and do nothing else. It will go, that's a dog. That's a face of a dog. Found another dog face. Look at that, dog face. And that will be the culmination of years of research, but it's still pretty incredible. I mean, you got to walk before you can run, but it's kind of funny to think about. These people are, doing their doctoral thesis on getting a computer to recognize dog faces. Anyway, before we get too sidetracked, um, we need to tell the computer when to start the program. So we go over here to the events, and there's this one block right here. When the green flag is clicked, just go ahead and slap it to the top, and that is our starting point. That is where we tell the computer explicitly where to start the program anytime we click the green flag. Now, here's the tricky thing. Certainly, you can certainly attach this to multiple different strings of code, blocks of code, in multiple different sprites. All it's going to do is just going to look for all of them and start running everything more or less at the same time. But the important thing is to think of it now as a starting point. As soon as the program starts, start running everything that's underneath it in order. So let's go ahead and do that. I'm going to click the green flag, and he's just going to kind of boop, and he's going to move ever so slightly, like almost imperceptibly. Click it again, and he moves a little bit more, and he says hello, and then it stops. Click it again, he moves a little bit further, he says hello, and it stops, and so on and so forth. I could keep clicking it, and over time I could, obviously, I mean, I can see him moving, but I could really get an idea for the difference in position by clicking it a few times. And there he goes. Now he's almost to the edge now. Now, really quickly, no, not really quickly. Let's go ahead and call this right now because I want to make sure that I can get you guys' questions in before I have to leave for my high school class. I know this was a little bit slow today, but that's how introductory things tend to go. Also, I apologize. I can just ramble on about computer stuff forever. So that was partly my fault. But hopefully things were a bit interesting. Hopefully you learned something new. Hopefully everything that we did today made sense. Our whopping 3 commands. On Monday or Tuesday, we're going to spend more time with Scratch, but we're going to make a lot more progress. So as we get going, as you guys, this is the language that the Raspberry Pi uses. Yeah. So the question was, this is the language used in Amazing Mechatronics. As far as I know, now it wouldn't necessarily be a bad idea to email Mr. Dubik and double check with that. Um, because especially because he will also post like an FAQ with an answer to that question for everybody else to see. But Raspberry Pis can use Scratch in order to interface with the GPIO pins that exist on them, the general purpose input-output pins that I was talking about last time. So you can use Scratch in order to program your Raspberry Pi to do stuff. Oh, actually, Victor, if you could email engineersoftoday@gmail.com, that email address with that question, they'll be more than happy to give you all the information because that'll come straight from Mr. Dubik himself, and he'll give you like a list of outlets and stuff like that that you could potentially get the Raspberry Pi from and all that kind of stuff. Anyway, let's go ahead and do the poll questions real quick, and then we'll do more question and answer, and then I'll have to leave for my high school class. But definitely, I'm glad that we did this. I enjoyed this. I hope you guys did too. Um, and yeah.